Alright, so let me start with an announcement. And that is that assignment 3 is now online. And it's due next Friday. And the other thing is, I could not find the mistake that I made last time. So I don't know if anybody else was able to find it. So I wasn't. So let's start with a summary now of what we did find last Monday. So given a continuous transformation, if we write an infinitesimal transformation as qi primed is equal to qi plus fi delta epsilon, and t primed equal to t plus g delta epsilon. So given such a transformation, if the action S is unchanged under this transformation, then the quantity capital Q that's given by the sum of I equals 1 to n of Fi Pi, or Pi are the generalized momenta, plus the second term, which was the sum from I equals 1 to n of Pi Qi dot minus L times G, is a constant or conserved. Okay. So this first term here is associated with the transformation of the coordinates. And the second term is associated with the transformation of time. And it's actually exactly the same term as what we called the Jacobi integral. So recall that if we found that if dl by dt equals 0, so if the Lagrangian doesn't depend explicitly on time, then we define this quantity H, which happened to be the sum of I equals 1 to n of di L by di Qi dot minus L was equal to a constant. And that's the Jacobi integral. Because di L by di Qi dot is the definition of PI, the generalized momentum. Okay? So this thing was called Noether's theorem. So we're going to finish up this chapter by looking at a few common transformations that leave the Lagrangian unchanged, or the action, and then we'll see what conservation laws they lead to. I should note that what we saw at the end of the last lecture was you can consider whether the transformation changes the action or the Lagrangian. So if it changes the action, that's the most general possible scenario. And it turns out you have to consider the change on the whole action to get the second term, the term with the G, the blue term, that gives you the relation with the conservation of time. But you can also consider whether the Lagrangian is unchanged. And of course, if the Lagrangian is unchanged, then certainly the action will be unchanged. And we saw that in the case of the coordinate transformations, one often only needs to consider whether the Lagrangian itself is unchanged. And then you end up finding that the conserved quantity is the first term, the red term. Okay? So let's do a few examples. Was there any questions about that? Okay. So let's do an example of translational symmetry. So let's say that the Lagrangian is invariant with respect to a translation symmetry. So what I mean is that you can define new variables Qi primed that are equal to the Qi plus Fi delta epsilon. So for example, for a translation in the x direction, we already did this in the beginning of the chapter, right? We looked at the translation. We looked at what the FIs would be for a translation and a rotation. So for a translation in the x direction, the transformation would be that x prime equals x plus delta epsilon, y primed equals y, and z primed equals z, and then obviously t primed equals t. So what we have is that f1, which is fx, is equal to 1, and then f2 equals to f3 equals to g. And that's equal to 0. So if we just apply Noether's theorem, we find for what is the conserved quantity in this case, well, the conserved quantity Q is equal to the sum from I equals 1 to n, so in this case it's 3, of Fi Pi plus G times the sum I equals 1 to n Pi Qi dot minus L. Okay, so G of course is 0. And this sum here, all the f's are equal to 0 except f1, which is fx. So this whole thing here is fx px, and since fx is just equal to 1, is px. So if we put that into words, if the Lagrangian is invariant with respect to translations of the x-axis, then momentum in the x direction is conserved. So a very obvious example of a Lagrangian that is invariant with respect to translation in the x direction is a Lagrangian where the x-coordinate doesn't appear. For example, the Lagrangian for a particle in gravity, right? You have the t, which is going to have x dots, y dots, and z dots. Then you're going to have the v term, which is just depends on z, so now x and y. So that clearly is not going to change if you move the x-axis around. And in that case, momentum in the x direction is conserved. So this does tie into the concept of a cyclic variable, the x not appearing, and its associated momentum being conserved. But it's much more general than that. So this tells us in general now that if the Lagrangian is invariant to translations in a certain direction, then momentum is conserved in that direction. That's a very powerful statement. Okay. Let's just add a new page. Let's do another example. Let's consider rotational symmetry. So, recall we did this at the beginning of the chapter. For an infinitesimal rotation of angle delta epsilon about the z-axis, we found that fx was equal to minus y, fy was equal to x, fz was equal to 0, and g was equal to 0. That was one of the examples in the beginning of the chapter 5. Right, where we made the approximation that as delta epsilon was small, sine of delta epsilon is roughly equal to delta epsilon, and cos of delta epsilon is roughly equal to 1. Okay. So the conserved quantity, so let's say that the Lagrangian doesn't change when you make this change of coordinates, then the conserved quantity Q. So it's going to be the sum over I equals 1 to 3 of Pi Fi. I'm not going to write the term with the G in it since G is equal to 0. So if I write this out, then I have minus y times px plus, well, if I'm writing in that order, x times py. All right? Now recall, angular momentum is defined as R cross P. There's not meant to be a dot there. Okay. So the z component of angular momentum is xpy minus ypx. Of course, these guys are the same. This is another statement you might have heard. If the Lagrangian is invariant with respect to rotations about an axis, then angular momentum about that axis is conserved. When I say angular momentum about that axis, I mean the component along that axis. Okay. So Lagrangian is invariant with respect to a rotation of the axes, then the angular momentum along the direction of that rotation is conserved. So for example, think of a planet orbiting the sun that happens in a plane, right? So Lagrangian is not going to be any different if you rotate your coordinate system in that plane, right? So as long as you keep the z-axis, for example, pointing perpendicular to that plane, it doesn't matter which way x and y point, the Lagrangian is invariant. And of course, for a planet orbiting the sun, angular momentum is conserved. So it's incredibly deep statements that these symmetries, these purely mathematical properties, lead to conservations of physical quantities that we know of. But this is really the fundamental mathematics that underlies classical mechanics and then ultimately carries over to quantum mechanics. So the third case, which we've already done about 3 different ways now, is time symmetry. So in time symmetry, we have all the Fi's equal to 0, and we have G equal to 1. So a translation in time means that T prime is equal to T plus a little bit. So we just change when time equals 0 that's a translation in time, right? So the conserved quantity, so this is a translation in time. The conserved quantity, so this time I won't write out the sum of the FI's PI's, is the sum from I equals 1 to n of PI QI dot minus L. And we saw that that was equal to what we called H, the Jacobi integral. I'm having trouble writing here. And the Jacobi integral is often equal to E, the total energy. And we showed that a couple times already, which is equal to T plus V. So here again, formally we now see that if the Lagrangian is invariant with respect to time translations, so an obvious case of that happening is if time doesn't appear explicitly in the Lagrangian, then clearly the Lagrangian is unchanged when you change time, right? So if the Lagrangian does not depend on time, then energy is conserved. Let's write that out in English. If the Lagrangian does not depend on time, energy is conserved. When I say that last statement there, it's a little bit restrictive, because in principle I can add the total time derivative to the Lagrangian, and then it's not necessarily energy that's conserved. So the Lagrangian could depend on time in a complicated way, so that when you add a total time derivative, the action is unchanged. And then the quantity that's conserved is not necessarily equal to T plus V. It is equal to PI QI dot minus L times G, but it might not be equal to the total energy anymore. But if the Lagrangian itself does not depend explicitly on time, then it is equal to energy. Energy is conserved. And so again, this makes physical sense, right? As usual, think of the example where gravity changes with time. So if the force of gravity changes with time, then time appears explicitly in the Lagrangian, because you have to know what time it is to calculate the potential. In that case, of course, energy is not going to be conserved. Okay, so any questions about that? So that was sort of the start of our going deeper and deeper into a very mathematical and analytical study of classical mechanics. So now it's going to get much more mathematical as we go into the Hamiltonian and we just observe mathematical properties that hopefully give you a deeper understanding of quantum mechanics. Okay, so now we're going to go to Chapter 7. So we're actually skipping Chapter 6. Chapter 6 is on the applications of the Lagrangian. When I look at how many weeks we have left in the course, I don't think we'll actually get back to it, but I highly encourage you to read it. In particular, the part about the first part on motion and central potential. So that applies a lot of these ideas. And one of the examples is two planets orbiting each other. So in principle, there's 6 degrees of freedom, right? Because you have two bodies in space, so each with 3 coordinates. And it turns out that through symmetries, you can find that angular momentum is conserved, and you can find a clever change of variables that reduces this problem from 6 degrees of freedom down to just 1 degree of freedom. And so it's actually mathematically quite interesting and not so difficult to rederive things like Kepler's laws and showing that the orbits are, what was the term? Ellipses and parabolas and hyperbolas, conicals, to show that you have. Chapter 6 should be posted. I did update the website probably yesterday, so it could be that you haven't seen it. But I've updated the course. I've added some of the video lectures that was missing. For some reason, the YouTube one for Monday crashed. But now we have all the material online. No, you're right. Chapter 6 is actually not posted. Okay, I will post Chapter 6. But I have posted now Chapter 7 and 8. And 9. You're right, Chapter 6. Okay, yeah, I'll make a note. I'll post Chapter 6 today. Thanks for pointing that out. So, Chapter 7, the Hamiltonian. At the end of the course, I will also actually post the whole textbook as one big file. But since I was still editing as we go, I didn't post it quite yet. Okay, so the Hamiltonian, if you haven't seen it in classical mechanics, I think by now you have taken some quantum mechanics and you have seen the term Hamiltonian. So it should have appeared in quantum mechanics, and now we'll see that it also exists in classical mechanics. I know some of you haven't done this version of classical mechanics yet. So let's just recall mathematically what we've done so far in the Lagrangian formalism. We describe a system using n coordinates, qi, and we use the Euler-Lagrange equation to get second order ODEs, ordinary differential equations, for the qi as a function of t. So let me say explicitly that the qi is dependent on t. Okay? And in order to solve a problem, need to specify initial conditions for the qi and for the qi dots as a function of t. So mathematically, right, we have second order differential equations. So if you have to solve a second order differential equations, you need initial conditions both on the quantities and on their derivatives. Physically, you can think of it as the system could be, for example, a cannon firing a cannonball. So the system, a cannonball moving through the air, is described by a Lagrangian. But the ultimate path that the cannonball will take depends, of course, on the initial position of the cannonball, but it also depends on the initial velocity of the cannonball. So you must specify, even though you only have one variable that you're solving for, the position as a function of time, you need to specify initial conditions on both those variables, the positions, and their velocities. And that's because the ordinary differential equations of motion of the equations of motion, so our second order differential equations. Okay? So what we're going to look at now is the Hamiltonian formalism. So in the Hamiltonian formalism, we describe the system using n coordinates, qi of t, and n momenta, pi of t. So of course, that's a total of 2n functions of time that we need to solve for. So what we've done is we promote the generalized momenta to the same status as a coordinate. Earlier we had a coordinate in the Lagrangian system. We had the derivative of that coordinate with respect to time, which we called velocity, and then we could write out the Lagrangian. But the whole thing was still an equation for the coordinate, right? So in the Lagrangian formalism, we're describing the system in what we call configuration space. In the Hamiltonian formalism, we call this phase space. So the cannonball in configuration space you need to specify as x, y, and z coordinates. In phase space, you need to specify its x, y, and z coordinates and the x, y, and z components of its momentum, or the three generalized momenta, which might not necessarily be linear momenta. So that's a fundamental difference. So we've promoted pi, the momenta, as one of the variables that describes the position of the system in what we now call phase space instead of configuration space. So configuration space in normal 3 dimensions is 3 dimensions. Phase space in normal 3 dimensions of space is actually a 6-dimensional space. So that part's annoying because we now have to solve for 2n different variables. But then the part that's easy is now we have 2n first order ODEs. So instead of having n second order ODEs, we'll end up having 2n first order ODEs. But mathematically, we know that's equivalent, right? You can always write a second order ODE as 2 first order ODEs. That would generally be actually how you solve it. So it's not fundamentally that different, except that the fundamental description of promoting momentum to one of the variables that describes the system is important, is fundamentally different. Okay, for the order EDs. And then in this case, we need to specify the initial conditions only on the 2n variables. So it doesn't sound like it's different because we still have to specify 2n initial conditions, but we're specifying the initial conditions on the variables, not on their derivatives. So in the Lagrangian formalism, we have to specify the initial conditions of the position and of the velocities. But here in the Hamiltonian formalism, the system is described by position and momentum. You have to specify both. And so you specify an initial condition for the momenta and for the positions. And so that means that the trajectory in phase space is completely determined by its initial position in phase space, because the initial position in phase space includes both the positions and the momenta. The Hamiltonian, or the Lagrangian, will determine the shape of that trajectory in phase space given a particular starting point. So that's not true in configuration point space, three-dimensional configuration space. You can start anywhere in the space, and the Lagrangian will not determine which path you take until you specify the initial velocities as well. In phase space, all you have to do is specify that initial point, except that that point is 2n-dimensional. But then the Lagrangian, or the Hamiltonian, as we'll see, specifies uniquely the trajectory that that point will take in phase space. This is a key thing to understand, and we'll come back to that later when we look at Liouville's theorem. Okay, so that's the introduction. So we're going to do an aside now on what's called the Legendre transform. So this is section 7.1. So it's going to be a mathematical aside on what's called the Legendre transform. And you've probably already seen this, maybe without knowing so, though. It comes up in technically chemistry, but thermodynamics, when you calculate different quantities. Maybe in some cases you're interested in knowing how a system evolves with pressure and volume, but maybe in some other problem you want to know how the system depends on pressure and temperature. And so then it depends whether you should consider the entropy or the Gibbs energy or the, I don't actually remember all the terms, but those are just different ways of calculating the energy of the system using different sets of variables. Maybe you're interested in pressure and volume, maybe you're interested in volume and temperature. And so the Legendre transform is actually what relates those different calculations of energy so that you can use different quantities to calculate them. So if you Google this, you'll find probably examples that have to do with chemistry. So let's start with a simple example. Okay, so forgettable mechanics for now. This is a purely mathematical aside. So given a function f that depends on a bunch of variables, which we'll call u1, u2, and up to un. Define new variables vi, and we define the vi to be the partial derivative of f with respect to ui. So there's as many vi's as there are ui's, right? So you have this function, it could be anything, it could be a Lagrangian, and then you define new variables that are the partial derivatives of that function with respect to the old variables. Okay. So the Legendre transform g of the function f is defined to be g equals the sum over I of ui vi minus f. That's a definition. And the whole point of this Legendre transform, and what's really neat, is that g only depends on vi, not on the UI. That's not super intuitive, right? Because clearly the U's are in the definition of G. So somehow G doesn't actually depend on the U's, it only depends on the V's. So let's prove that. We'll prove it 3 different times. All right, proof. So if it doesn't depend, if G doesn't depend on the UI, if you vary the UIs, then G should not vary. So that hopefully hints towards that we should calculate what the variation of G is. So consider delta G. All right, so that's delta of the definition that we have. Sum I equals 1 to n, ui, vi, minus f. Okay, so if I do that variation, I get the sum from I equals 1 to n of the product rule. So I have ui delta vi plus vi delta ui. And then I have minus. So now f only depends on the UI, right? So the variation of f is the sum over I is 1 to n. It's just the chain rule of di f, di ui, delta ui. Right? The variation of f, I break it out into the sum of the variations of all the different variables that it depends on. Okay. So let's group the terms that depend on delta vi and the ones that depend on delta ui. So it's the sum from I equals 1 to n. So there's only one term that depends on delta vi, so it's delta vi. And then it's plus the sum from I equals 1 to n. I'm going to factor the terms that depend on delta ui. So I now have vi minus di f by di ui delta vi. Right? I just factored out the delta vi there. I'll recall the definition now. That vi is actually defined to be di f by di ui. Hence that last term is actually equal to 0. And so what we find is that the variation of G is given by a sum from y equals 1 to n of ui delta vi. So it doesn't actually depend on the variation of the u's. So in other words, you change the u's, it's not going to change G. So we conclude that G is a function only of the VI. So we write that as G is a function of VI. So if G is only a function of the VI, then I can write delta G, just as I did for delta F above here. Delta G is going to be equal to the sum from I equals 1 to n of di G by di VI delta VI. Right? That's simply the chain rule. Since G is only a function of the VI, and very generally, I can write delta G equals the sum of di G by di Vi delta Vi. But the thing that we have on top is also delta G. All right, these two must be equal to each other. All right, so this is exactly the same thing. So we conclude, so if I look, right, both are a sum over I of something times the delta Vi. So that something's got to be equal to. So we find that Ui is equal to di G by di Vi. So that's very interesting. So it gives us the choice of describing that system that's described by the function f. We can either use f and as variables the u's, or we can equivalently describe the system with the function g and using the v's. And the Legendre transform is how do you go from one to the other. So the Legendre transform so if we have the f of the ui's and the g of the vi's, then we can write that the Vi is equal to di f by di ui. The ui is equal to di G by di Vi. We can write that G is equal to the sum of the Ui Vi minus F. And we can write that the F is equal to the sum of the Ui Vi minus G. That's just the same equation, right? And so we call this the Legendre transform. So this is a prescription from going from a one description using f and the variables u to another description using g and the variables v. And like I said, this comes up in chemistry when you're looking at like the Gibbs free energy and things like that. Is the sum, no, so the sum does not include the f and the g. I mean, if you want a flavor of what's to come, right, this is exactly like the Jacobi integral. So the sum of the ui vi, the ui is going to be the pi qi dot, and the f is going to be L. This is going to give us a prescription from going from the Lagrangian to the Hamiltonian. In equation 7.3. Yeah, so that's because equation 7.3 is up here, right? So that's this part here. So here what I've done is delta F is equal to the sum from I equals 1 to n of di F di ui delta ui. So that's where the sum came in. All right, so in the line above it here, I have delta of the sum minus delta of f. And then when I do delta of f, since f depends on multiple variables, I have to use the chain rule. Okay. All right, so let's do this whole thing again. But now let's suppose f is a function of two sets of variables. So let's call them u1 all the way to un and w1, w1 all the way to wn. So two sets of variables. So again, a flavor of what's to come, the Lagrangian could depend on two sets of variables. It could depend on the QI's and the QI dots, if you consider the QI dots as independent. Okay. So again, let's define a new variable, VI, to be given by di f by di ui. And so what we do there, we actually say that the ui are the active variables, and the wi are the passive variables. So the active variables is the one that you, eventually you'll see that we get rid of them and we transform from the UI, from the U's to the V's. And the W's, as we'll see, are unaffected. Okay? So then the Legendre transform G of f is given by the exact same formula. It's the sum from I equals 1 to n of ui vi minus f. So the f is not in the sum yet. Okay? And just to be explicit, the f depends on the ui and the wi. So again, I'm going to make the same claim that G actually only depends on the vi and the wi. So G does not depend on the UI. And so we'll do exactly the same proof. So consider delta G. So that's delta of our definition, equals 1 to n ui vi minus f. Right. So that's equal to, if I work on the first term, I equals 1 to n of, just apply the product rule. So I have ui delta vi plus vi delta ui. Now remember, f is a function of the ui and the wi's, right? So when I do delta f, it's minus the sum I equals 1 to n, when the variation of the f is di f by di ui delta ui plus di f by di wi delta wi. I made a simplification here where I'm assuming that there's the same numbers of U's as there are W's, right? So clearly there has to be the same numbers of U's and V's, right? Because VI is di-F by di-UI. But there's no real restriction on the number of U's being equal to the number of W's. The W's are these passive variables that they are not involved in the transformation. So it's just easier if I write them out as the same sum and I assume that there's the same number of them. But there doesn't necessarily have to be the same number. Okay. So I do the same thing now. I group the terms. So the first, oops. So I'm going to keep the delta U's and then group the other two. So first I'll group the ones that don't have delta U's in them. So sum from I equals 1 to n. I have UI delta VI minus the term with the delta W's in it, which is di-F by di-WI delta WI, and then plus the sum from I equals 1 to n of now the terms with delta UI's in them. So I have VI from the first term, and then I have minus di-F by di-UI from the second term. Apologize for my U's looking an awful lot like W's. Okay. So again, this term here equal to 0 because VI is defined to be di-F by di-UI. And so I find that delta G is equal to sum from I equals 1 to n of UI delta VI minus di-F by di-WI delta WI. And so you see here that the delta G doesn't have any delta U's in it. So when you change the delta U's, G doesn't change. So indeed, G is now a function of the VI's and the WI's, not the UI's. So now we want to write out the laws for the transform from going back and forth between F and G. So since G is a function of VI and WI, we also have the delta G has to be equal to the sum from I equals 1 to n of di-G by di-VI delta VI plus di-G by di-WI delta WI. That's just the definition, practically, or the chain rule. So again, we do the same thing. We can compare the terms that have the terms in delta VI and terms in delta WI. And so what we find is that UI is equal to di-G by di vi, and we find that di f by di wi is equal to minus di g by di wi. And of course, we still have the transformation equations, right, where f is the sum of the ui vi minus g, and g is the sum, of the ui vi minus f. So that's the Legendre transform. It allows you to go from f to g using a different function to describe the system using different variables. If the functions are related with the Legendre transform, then the different variables are related to each other according to these equations. I guess I forgot to write down the equation where vi equals di f by di ui. And put that one in there. Okay, any questions about that? So let's do it one more time now, but instead of using G and F, we'll use L and H. So let's do the Legendre transform of the Lagrangian. So the Lagrangian L is a function of the qi dots, and t. Okay. So let's choose the qi dots as the active variable. And we'll leave the qi and the t as passive variables. So here's exactly an example where there's not the same numbers of u's and w's. Right? The u's, the active variables, are the qi dots, and the w's, the passive variables, are the qi's and t. Right? You can call those all w's. So here's exactly an example where there isn't the same number of each variable. All right, so let's just blindly consider this Legendre transform. Okay, so we introduce a new variable. So the variable is going to be equal to di-L by the derivative with respect to the active variable, which is qi dot. So the new variable that I'm going to introduce is di-L by di-qi dot. So a good name for that variable would be P. Okay, so this is this exact same thing as when we said that the VI was the di-F by di-UI. Right. So I'm choosing the dots, the qi dots, as the active variables, and I'm introducing a new variable that's the function L divided partial derivative with respect to that active variable. Right. So then L is like F in what we just did. All right. So in that case, I introduce a new function, the Legendre transform of L, and I'll call it H. So I already know that H is not going to depend on the Qi dots, right? We just proved that. So H is going to depend on the Pi, the Qi, and T. So it's going to depend on the new active variable, or the transform of the active variable, and then the passive variables. So I remove the Qi dot, and I put in a Pi. So that's the Legendre transform is going to be the sum from I equals 1 to n of Pi Qi dot minus L. Alright, that's exactly the same as the sum of the Ui Vi minus F. So that's interesting, right? Because you already recognize that Pi Qi dot minus L is the Jacobi integral. So it's interesting how all this stuff fits in. Okay. Alright, so now we need to know the transformation equations that go from H to L. So we want two different descriptions, in this case of classical mechanics, using a Legendre transform. So we know from what we just did that if we have a function that defines a system with respect to using some variables, we can go with a Legendre transform to a different function that describes the same system with a new set of variables. So we're going from the Lagrangian that describes a system with Qi dots, and T's, to the Hamiltonian, H, which describes a system using Pi, Qi, and T. Okay? So to get the transformation equations, we'll just do it exactly the same way as we did before. We'll consider delta H. So delta H, and I'm going to redo the same derivation again, because in this case, we're not actually doing the case where the Wi's are at the same number as the Ui's, right? Because we have an extra T in there. So that's going to be delta of the definition, which is delta of the sum from I equals 1 to n of Pi Qi dot minus L. So if I take that variation, I get the sum from I equals 1 to n of Pi delta Qi dot plus Qi dot delta Pi, and then minus, now I have to do the variation of L. So remember, L is a function of Qi dot, and T. That's minus the sum from I equals 1 to n. I have di L by di Qi delta Qi plus di L by di Qi dot delta Qi dot. And then L also depends on T, right? So then it's minus di L by di T delta T. So that term is outside of the sum. So I'm going to again rearrange the terms so that I group the terms that have delta Qi dots together, since those are the active variables. So that's equal to the sum equals 1 to n of Pi delta, oops, that's the one that we don't want. So here we have Qi dot delta Pi minus di L by di Qi delta Qi minus di L by di T delta T, and then plus the sum from I equals 1 to n, factoring the term with a delta qi dot. So here I'm going to have a pi minus a diL by di qi dot delta qi. And then as usual, this term here cancels. Because the pi, of course, is defined to be diL by di qi dot. So I've run out of page. So that gives us that delta H is given by the sum from I equals 1 to n of qi dot delta pi minus diL by di qi delta qi minus diL by di t delta t. Now recall, since h is a function of pi, qi, and t, we can also write the variation using the chain rule, so that's got to be equal to delta h equals the sum from I equals 1 to n. We have di h by di pi delta pi plus di h by di qi delta qi, and then outside of the sum plus di h by di t delta t. So now again, we compare the terms that go with the delta pi's, the term that goes with the delta qi's, and then the term that go with the delta t. So what we find is qi dot is equal to di h by di pi. We find that diL by di qi equals minus di h by di qi. We find that diL by di t is equal to minus di h by di t. Those last two equations are the equivalent to the ones that were the derivatives with respect to the passive variable. So that's why they both have a minus sign. So it's still completely equivalent. And then on top of that, we also had pi was equal to diL by di qi dot. And we had L is equal to the sum from I equals 1 to n of pi qi dot minus h, and h is equal to the same thing, I equals 1 to n pi qi dot minus L. So there you have it. That is how you transform from the Lagrangian to the Hamiltonian, where the Lagrangian is a function of qi and qi dot. So we can describe a system using either a function L of qi dot and t, or two, Hamiltonian, which depends on pi Qi, and T. So this is, of course, the Lagrangian. This is the Hamiltonian. And at this point, of course, it's only mathematical trickstery. And I haven't really talked about what this Hamiltonian could possibly mean physically, or how you could actually use it in a physical problem. But we'll see that next lecture. Okay, so what we derived today is the transformation equations that go from a description of the Lagrangian using the coordinates and their velocities to description using a new function, which we'll call the Hamiltonian, using the coordinates and the associated generalized momentum. Any questions about that? Okay, well, next time we'll start from here, and we'll look at what are called Hamilton's canonical equations, which are the equivalent of the Euler-Lagrange equations. So they're the equations that give us the equations of motion. All right, thanks everyone for joining. We'll talk again on Monday.